Learn about physics, young people often get all excited about the centrifugal force because they learn very early on that it doesn't exist, and so they get very excited by that. And any mention of centrifugal force is immediately challenged with, oh yeah, but it doesn't exist. Well, they're not entirely wrong, but they're also not entirely right. I can measure the centrifugal force. It is a force that has a real effect on the world around me. I can see the effect of it. So it's not true to say it doesn't exist, but obviously the nature of it is a little bit more complicated, a little bit more exciting than just a force that pushes outwards. I think we're going to need this. What's our record collection looking like? Hymns for Little Children, maybe not. What's this one? Stethoscope heart record, brilliant! Let's put this banging record on. Now, just the act of putting the record on is going to cause controversy on the YouTube channel, in the comments section. I just know it. There's going to be people who are upset with how I do this. Nothing quite induces emotional responses quite like vinyl. So, let's get the speed knob and let's see if I can increase the speed. There it go. Turn it up. Let's listen to this banging tune. Oh, there's the drop. High tempo. And that's a record that's skipping right there. Ah, what a beat. So the reason for this record player, bought this dirt cheap from a charity shop because I needed a reliable, constant angular velocity turntable to do circular motion experiments on. And here it is. I removed a tiny little potentiometer that was used to control the speed on one of these settings and replaced it with a much bigger one that I could handle on this outside here. So I modified this slightly so that I can get some quite high angular speeds on this thing that I can reduce with this little potentiometer over here. So that's a fairly low speed. Angular speed, somewhere in the middle, getting higher and higher and really high. So we can do experiments on this to investigate circular motion. Now I wanted a nice flat surface to play on, so I went to a charity shop and I did buy this. This is the most dreadful album I could find, but if you like this sort of thing, then my apologies for being so insulting. This is truly dreadful. If I'm going to get a copyright claim on this video because of the use of Hymns for Little Children from 1970, I don't know when, 1967, including such bangers as All Things Bright and Beautiful and Jesus Wants Me for a Sunbeam, then, I mean, so be it. I doubt there's anyone alive who could make such a copyright claim, but of course the copyright for this is actually owned by EMI. Who knows whether Captain Joy Webb of the Salvation Army's Sunbury Junior Singers from 1967, who knows whether he's still out there and he's desperate to get his pennies from this second-hand record. I don't know. But it gives us a nice flat surface to play on. truly dreadful, though. Oof. That's enough of that. So that is the turntable surface that I want to play on. I got this rubbish record because I'm not bothered about scratching it if things move around. We're going to play a fun game called When Does the Blue Tack Fly Off the Record? And I'm just going to place bits of blue tack on this record on different tracks. I mean, they're not all going to be the same bits of blue tack. It'd be lovely if they are, but they're not. This is not exactly a rigorous scientific activity. Certainly not a fair test, but I'm just putting the bits of blue tack on here. The blue tack sticks ever so slightly to the record. I'm not pushing down on it, but it does stick ever so slightly. And that's going to mean that there is a force between the surface of the record and the blue tack. Just like that, which should increase friction between the record and the blue tack. Let's put one right in here. Right, let's get these spinning. And you can see that at this slow speed, none of the bits of blue tack are flying off. Now, just a minor thing, you'll notice it takes the same amount of time for each piece of blue tack to make one complete cycle, to make one complete circle. That's because it all has the same angular speed because it's all attached to the same rigid disc. Now let's move around here and increase the speed slightly. Bit more. Oh, am I on the wrong setting? Never remember which way to turn it. I need to write on this. Ah, there we are. Oh, we've lost one. We've lost two. We've lost the two outer bits of blue tack already. And some of the others appear to want to move, but the ones near the middle, they're holding fast. Let's turn it up a little bit more. Oh, we've lost a few more, but there's three still in the middle that have not gone yet. Let's just turn it up a bit more. Oh, we've lost another one, but these two, they're doing okay. Oh, is that the highest speed it can go? That's the highest speed it can go, and those two bits have held on. So what's happening here? Well, for these blue tack bits to be moving in a circle, there has to be a force acting on them in towards the centre of the circle. There has to be. That is the centripetal force. Right, now let's use this shiny piece of plastic. Let's draw an arrow. I wonder whether I can use this arrow to demonstrate what I'm trying to demonstrate. This is going to be the latest in computer graphics or something. Where is it? There it is. Oh, I'm miles off. It's going too fast. Can I go any slower? No, that's faster. Oh, that did not work at all. Sometimes I can be really dopey. Right, there we go. There's a piece of blue tack. The arrow's pointing towards the centre there. That's the direction of the acceleration of that piece of blue tack. Let's just move the other bits of blue tack off it to make it clearer what's going on. That arrow indicates the direction of the acceleration. Because F equals ma, F is proportional to a for a constant mass, which it is, then the force acting on that piece of blue tack is towards the centre. What is the nature of that force? Well, it is a adhesive force, I suppose you'd call it, because this is, you know, blue tack. But if you just place any old object down there, it might be a friction force. Let's go change the object out. So here's a lid from a bottle. That's all it is. Place it on there. It's moving in a circle. Now that's definitely a friction force that's acting on that to cause it to go in a circle. And if I just blue tack this little arrow on it so you can see what the direction of that force is. There we go. Just like that. Managed to make the arrow a bit darker. And there we go. So that's the force of friction acting on this lid to keep it going in a circle. Now what happens if the angular velocity gets too high is the force of friction required to cause circular motion gets too high, and then the lid flies off because there's a maximum force of static friction. So let's turn this angular velocity up. Let's just move around here. Turn the angular velocity up. Oh, I'm on the wrong switch. Oh, sugar, that's too high too soon. Scratch up this record, cause a lot of people to be very upset. Here we go again. So force of friction is going to increase as I turn this knob. It's going to increase. And if you wanted to, you could measure the angular velocity of that, because we could time how long it takes to do one circle, or we could time how long it takes to do, let's say, 10 orbits. Divide that by 10, that's the time period, and 2 pi divided by the time period is the angular frequency. And we could measure the radius from the centre to there and say that at that particular radius, what is the angular frequency that causes the required friction on this object for it to be going in a circle to be greater than the maximum static friction. Let's just increase it a bit more. Oh, and it's somewhere around there-ish. It's very, very fine control. I need a better pot. But I can move it closer, and that would be a higher angular velocity where that happens. And I could move it further away, and it would be a lower angular velocity where that happens. In fact, I might not even be able to get it to stay on, even at the lowest angular velocity. Let's just increase it a tiny bit. Increase a tiny bit more. Tiny bit more, tiny bit more, tiny bit more. There we go. So, you know, we could do that as an experiment. I'm tempted to do that as an experiment in a separate video, but that's not what we're focusing on in this video. In this video, we're focusing not on centripetal force, which in this case is the static friction. We're focusing on the centrifugal force. So I'm going to record this in slow motion with the little lid spinning around, increasing the angular velocity until we see the little lid spin off. So this is going to be in slow motion. This part of the video might be a bit long, so I might have to edit it. Increasing the angular velocity until this flies off. And I want you to look at what this does when it flies off. Now, what you probably noticed, or what you hopefully noticed, is that the object didn't just fly directly out. It maintained its forward velocity. Actually, these went in a curved path, and that's for complicated reasons that I don't really want to go into. Let's try the blue tack in slow motion. And just show you that it's not a thing to do with the lid. Let's just show you what happens with the blue tack when the blue tack flies off the record. Let's put it about here-ish, so it's going to fly off pretty reliably. Future Keith here. So the reason for the curved path is because of conservation of angular momentum. With the cap lid, the mass is mostly distributed around the edge, so it has quite a large moment of inertia. So conservation of angular momentum becomes quite important. With a body where the mass is closer to the centre, so a smaller moment of inertia, then we wouldn't have so much of a problem and we won't get so much of a curved path. Now, if you're interested in conservation of angular momentum, I could do a video about that some later point. It wasn't really the point of this video, and I forgot all about it when I recorded the video, so I was a bit irritated that I'd forgotten about it and the cap went off in a curve. So let's go and try something else. Okay, back to past Keith. Now, if you imagine we're stood on this round disc, if we imagine we're stood there watching this, then what would we see happen? Okay, we've got this ball which is in a certain position relative to us, and we're sat here watching this ball as we go around. We're watching it. What do we see happen? Let's make it easier to visualize. Let's cut out a little picture of a person. Okay, so here's a person. Imagine it is you, and this person is going to stand here Let's blue tack it in place and watch as this blue tack moves around in its circle, just like that. So that's the situation, staring at this blue tack, and let's imagine it spins fast enough, and what would they see? Well, from their perspective, they're not rotating, the rest of the universe is. And from their perspective, they're going to see the piece of blue tack fly outwards, whee, like that, all by itself. And they're going to think to themselves, what is the nature of that force? Well, that is the centrifugal force, pulling the blue tack outwards. Oh, how I'd love to say no records were harmed in the making of this video, but hymns for little children got quite badly scratched up. Oh well. Now this is the point usually where someone gets all excited and says, "But sir, you can't get centrifugal force. It doesn't exist." Well, let's have a little look at that, using the help of the Virtual Physics Laboratory 18 from Dr. John Nunn. So here you can see a simulation. Hello, that's my reflection in the background. And this shows a cannon and a target, and us trying to hit the target. Now, we can see that the ball moves in a straight line. Of course it does. Why shouldn't it move in a straight line? Newton's first law tells us that if the resultant force on the ball is zero, then its velocity should remain constant, and that's exactly what we see. The resultant force in the horizontal plane is zero, so the ball just rolls off in a straight line. And this is actually what we saw on that turntable, on the record player. But what does it look like to the track? I mean, if I just do this, I'm not sure if I can pause it, or I can't pause it. What does it look like when you're on the rotating track? So let's imagine that we're stood here. That's still rotating, but you're stood here. That little paper person is stood here looking at what's going on. Here you go. Let's just plonk you on there. So you're looking at this. Of course, you're rotating just like you were before, but you don't know you're rotating. And now, oh, how interesting. From your reference frame, it looks as though the ball is being pushed to the left. It looks like the ball is being pushed away. That looks a lot like a force acting on that ball in your reference frame. Of course, actually we know that that we're in a rotating reference frame and the ball is going straight, but from our perspective, the ball looks like it's going in a curved path. It misses the target. It ends up to the left, let's say to the left of the target. So if we do it like this, it ends up to the left of the target. Now the question would be, what is the nature of that force? What's the nature of that force that is apparently pushing the ball to the left and you only see it when you're on the rotating reference frame? Well, the answer is it doesn't have any nature. It's fictitious. We had things moving in a circle, and then we could describe the different types of force that can cause centripetal force. So if you consider a planet going around the sun, the centripetal force there is provided by the gravitational force. If you imagine our record player, it was the frictional force stopping the objects that were on the record player flying out to the edge. So we can name what type of force they are, but this force, this centrifugal force, which from our reference frame seems to be pushing these objects to the left, that doesn't have any nature. It's fictitious. Now, it is true that the magnitude of this force, this fictitious force, this centrifugal force, is equal to the magnitude of the centripetal force. But you cannot use any sort of Newton's third law argument, because that just doesn't apply in this situation. You cannot apply any Newton's law argument to try to explain the nature of that force because, well, it doesn't have a nature. It's fictitious. It's not really there. It's a consequence of our reference frame being non-inertial. Newton's first law, the idea of inertia, applies in inertial reference frames. Newton's second law, F equals ma, F is the resultant force, A is the resultant acceleration. We can only really measure them if we are in an inertial reference frame. Newton's third law, looking at forces in pairs between two bodies, that's got nothing to do with this. What we've got here is a non-inertial reference frame. That is to say, a reference frame where the rules of inertia don't seem to apply. A reference frame where, when the resultant force on the object is 0, it seems to change its velocity. That does not obey Newton's first law. Actually, it does, because Newton's first law only applies in inertial reference frames. This is not an inertial reference frame, because every point, every one of these white dots, is actually accelerating. It's moving in a circle. So each of those white dots is accelerating towards the center of this circle. I wonder if I can show the curved path again. No, it's not as clever as that. So we're going to attempt to measure the centrifugal force as we go around the roundabout in a car using one of these. Say, plumb bob on the end of a string, and as we go in a car around the roundabout with this suspended from the ceiling, we'll see it be pushed out to one side. By measuring the angle that the string makes to the vertical and knowing the mass of this thing, we'll be able to determine the force that, from our frame of reference, is acting on this thing to push it out to the left. That's what we're going to do. Okay. Going round and round and round. This is swinging a bit too much. Let's stop it from swinging. Try and keep it nice and steady. There we go. Look at that. Now, if you can, could you slow down and...
What speed do you want?
Slow down and stop.
Stop.
Just slow down and stop. So there is vertical. I'll try and hold the camera perfectly still. Yeah.
Give me a sec.
We all feel dizzy.
You've asked me to stop.
I know, I've stopped.
I was all right when I was going, but I can't stop like that.
It's horrible, isn't it? Right, whenever you're ready, let's go.
9 miles an hour.
So I've got a nice reference.
Right.
Oh, it's swinging to the left.
Right, so that was that's 9. 8, 9, no. Try to keep it constant. What shall I do?
Yeah, keep it. Well, it doesn't really matter what it is as long as it's. Oh, I feel sick. Right, that's
8 miles an hour.
It's swinging a bit. Let's try and keep it. We've got it at an angle. I could probably measure that. It's swinging too much again.
Oh my god.
Okay.
Right, I'm going to stop because I can't do that again.
Right, so what?
It's the recovery bit.
So what speed was that?
That was 8 miles an hour.
8 miles an hour.
I could possibly get it to 10, but it's a very small roundabout.
Should we try it?
I can try.
Let's try it. Let's go for 10.
Right. I don't know how successful I'm going to be at keeping it.
As long as no one else comes around the road.
I doubt anyone else is going to come round and look at this nutter that's going round and round the car park.
Here we go. Oh, I don't like it.
I can't get it to 10, I don't. That's 10.
Oh, look at it swing. That's, right, let's try and stop it from swinging too much. Right, that's, we'll have to average whatever that angle is, I think. All right, that's fine. Oh, you can stop now. You can stop now. Oh.
That's 10. Go faster.
Oh, it's moved. No, don't go faster.
I got to 12 and I feel sick.
Okay, we're done. We're done. Right. Cheap balance. Turn it on. Let's measure the mass of this thing. 38.21 grams. 38.21. So 38.21. That's grams. So let's divide it by 1,000. Let's multiply it by 9.81. And so that is the force, the weight acting on that plumb bob, 0.3748 newtons or thereabouts. Let's write that down. And I'll label that FV, the vertical component of the force. So what we're going to have is a plumb bob, which when hanging vertically downwards is being pushed downwards with that 0.3748 newtons of force, but it's going to appear at a different angle, like this. In fact, let me draw that just a little bit longer so it gets lined up, like that. Now the tension in the string is going to be acting in this direction. Don't know what that is, but we do know that the tension in the string plus the weight plus, from our reference frame, it looks like a centrifugal force acting horizontally to the left should form a closed triangle, badly drawn, should form a closed triangle. This is going to be our centrifugal force. All we need to know is what this angle there is. Because we know what this one is, and so we know that the tan of theta is going to equal FC divided by the adjacent, which is FV, 0.3748 newtons. And so once we've measured the angle, we know that the centrifugal force is 0.3748 newtons multiplied by the tan of whatever that angle is. Well, let's measure that angle. Well, there's the video with the string swinging around. You can see it stays at a pretty good angle there. And then after I stop, or after my wife who's driving stops, the string hangs vertically downwards. So let's measure that vertical. Hopefully this will work. Should just be able to place this on here and place an X there and an X there. And I connect those two X's later. Right, now let's see if I can get driving. Yeah, let's fast forward it to where we're driving. Swinging quite a lot, so that was the problem. That was pretty still there. And there, oh no, I've moved the video. Let's try that again. Come on. I'm going to try and keep the plastic as vertical as I can. Swinging around, swinging around, swinging around. Right, so it's about there. And that was at about 7 miles per hour. So there are the, whoops, there are the X's. Should be able to connect them. I did my best to keep the plastic vertical, but you know, you've got the video there, you can do this yourself. Oops, pen smudges a little bit. Like that. Get out our protractor to measure the angle. And I make that 16, to the nearest degree it's 16 degrees. That is tan 16, which I can type straight into my calculator. And I got a centrifugal force of that, 0.1075, or about 108 millinewtons. About 108 millinewtons of centrifugal force. Now, from my reference frame, it was a centrifugal force. From my reference frame, the plumb bob was pushed to the left. From my reference frame, I can measure what that force is. But of course, what's actually happening is the car is being pulled to the right. And so the mass is being pulled to the right. And it's being pulled to the right by this tension increasing as we go around that corner. This downward component of force doesn't change, but the tension is going to increase producing a resultant force. Now this is different because in this diagram it shows no resultant force. It shows the tension balanced with the weight and the centrifugal force. The idea being that the plumb bob sat there and from my reference frame did not appear to be accelerating. It just sat there. Actually it oscillated around that point, but if I was able to drive in a circle with a constant enough speed, it would settle at that point. So from my perspective, that was a centrifugal force balancing the other two to produce equilibrium. However, from an inertial reference frame, so that is outside the car, you can clearly see that the ball, the plumb bob, was accelerating. It was not actually in equilibrium. It was accelerating because it was moving in a circle and thus accelerating towards the centre of the circle, just like we saw with the record player. And so that means that there is a resultant force on it. And the resultant force on it, well, the tension is the tension. I can measure that with a Newton meter. That is what it is. And the weight doesn't change. So the resultant force is this. Our diagram shouldn't show an arrow pointing that way. It should show an arrow pointing that way. And Fc becomes the centripetal force. Well, the centripetal force doesn't have any nature. It's just what we call the resultant force when the resultant force causes circular motion. The centripetal force is the tension added to the weight. That's all it is. And so my centripetal force is this amount. It just happens to be to the right, not to the left. Now the equation for the centripetal force is F equals mv² over r. So we could use this to find the radius of the roundabout, because we know what v was. It was about 7 miles an hour. Not very accurate, but we'll do it anyway. So we can rearrange this like this. We knew the mass of the plumb bob, the speed was 7 miles an hour, I'll have to convert that, and F was the centripetal force, that was the 108 millinewtons. So I've substituted the numbers in. This is what 7 miles an hour was in meters per second, according to a quick Google conversion. So let's type all this in, 38.21, but it was grams, not kilograms, so let's do that. And then 3.129, it was squared times. That gave us a radius of curvature of just 3.48 meters. So it was a bit on the small side. Does seem a bit on the small side, but it was only a mini roundabout, so maybe it's not a million miles off. Obviously, 7 miles per hour, it might have been nearer to 8 miles an hour. Well, that's 8 miles an hour right there, so 38.21 times 10 to the negative 3 multiplied by 3.576 squared divided by 0.1075. That gives us more like sort of 4.5 meters, so somewhere between those two, about 4 meters. Actually, that's probably not far off what the radius of the circular motion was when I was going around, well, when my wife was driving around that mini roundabout. So it does check out. And you can do that experiment yourself, but I'll leave that there. We have measured the centrifugal force from the reference frame inside the car, in which we assume that the resultant force on the plumb bob was 0, with this mysterious, fictitious centrifugal force pushing the plumb bob to the left. Actually, that was a consequence of the plumb bob being pulled to the right as it went around a circle, but we couldn't see that circular motion because we happened to be undergoing the circular motion with the plumb bob. We were in the car as well, so we didn't see it. And that's similar to how the Lagrangian points are determined. When we look at things like Earth moving around the sun, well, we're on the Earth. We're on this reference frame that's moving in a circle. So we can find points where it looks like the resultant force is 0. Actually, that's not the case. There is a resultant force at that point on masses acting towards the centre of that circular motion. But it can be quite complicated to try to work out what's going on with that. So it can be easier to visualize our Lagrangian points if we, instead of talk about centripetal force, imagine this centrifugal force, this fictitious force, acting outwards, out of the circular motion.